So, hello everyone. I'm Vincent Reverdy. I'm a postdoc researcher at the University of Urbana-Champaign, and I am working in between numerical cosmology and computer science. And today I will present how we came from a very theoretical cosmological background and how we started to investigate bit abstraction in C++. I will try to summarize the talk in 3 slides. First, what is this talk about? So as Bryce explained on Monday, I think there are several levels of parallelism, and I will focus on bit level parallelism, which is the most fundamental one, which means that basically we want to process bits in parallel. This talk will be also focused on what's wrong with vector bool and std bitset, because there are a lot of problems with them in C++. And I will show how we can count bits 100 times faster than with std vector bool. So this work led to a library. It led to a library which is called the bit library, and it's very easy to use. So if you want to use it in less than 3 minutes, so you just download it on GitHub, and then you can start implementing your very simple example to run a minimal test case. For example, here we declare an unsigned int. We set it to 42. And then we will try to observe the bits of that unsigned integer. So we create a bit iterator on the address of the unsigned integer, and we at the beginning of it, and we call it first, and we create another one on the next unsigned integer. And then we iterate through the sequence of bit iterator. And in one line, we managed to display the bits of 42 between the least significant bit, starting at the least significant bit, and finishing at the most significant bit. And that's it. So the library is still evolving. So there will be breaking change, but our goal is to try to standardize it and to give people tools to manipulate bits both in a generic and in a very efficient way. So there is a description for the proposal. There is a proposal for the description of the project, and also a wording in progress. Then in the coming month, there will be breaking changes, but benchmarks are very welcome on that library. So now I will explain where we started in cosmology and why we ended up playing with bits. And to tell that, I will tell a story. So once upon a time, in a galaxy far, far away, on a small piece of rock wandering aimlessly in the vast universe, a team of astrophysicists was wondering about the nature of life, the universe, and everything. Because they knew some math, some physics, some computer science, and some programming, they decided to design a code that could answer their metaphysical question about the universe. They said, let's take an enormous box with periodic boundary condition, which means that the right and left are connected together, the top and bottom, same thing, and same thing for the front and back. And let's fill that enormous box with particles weighing the mass of millions or billions suns. That's a lot. Now divide this box in cells, and in that grid, we will apply the following recipe. So for each cell in that grid, we will first, for each cell that contains a particle at position x and velocity v, we first start by interpolating the density, calculating the density in each cell, depending on surrounding particles. From this density rho, we can compute the gravitational potential because the more mass you have, the greater the potential will be. Then from phi, we can interpolate back the acceleration at the position of particles. And from this acceleration, we can compute the new velocity of the particles. And from the new velocity, we can compute the new position. And doing this, step after step, we can see the particles moving. And using this very simple recipe, we can form galaxies in simulations. So simulating galaxies is nice, but it was not answering their question. So they decided to do better. Let's try to investigate larger scales with galaxy-sized particles. First, they took a supercomputer, and they made the box expanding as the universe does. And then they filled the box with a distribution of particles that is based on the statistics of what we observe in the cosmological microwave background. Fourth, to improve the first simulation, they made an algorithm, a mesh refinement algorithm, so that they have more resolution where they have more particles. So with this kind of scheme, they divide, they have a regular grid, and when they accumulate particles, they have threshold, and when one of these thresholds is passed, we divide the boxes into smaller cubes. And finally, after all this work, they ran their simulation using millions of computing hours over thousands of cores, and they ended up with this thing. So in that kind of simulation, every luminous dot in that box is of the size of a galaxy. And what we see is that there are structures, and if we compare that, large-scale structures, and if we compare that to what we observe, we see the same kind of filaments. It was nice and exciting, but to answer the metaphysical question, they needed far more computing power. Thankfully, new architecture and new supercomputers were coming. But they realized that there was a major problem, because their code would not scale up to millions of core. And a major part of the problem is due to data structure. So this slide is stolen from a talk from Chandler 2 years ago, 1 or 2 years ago, I think. And I think it summarizes very, very precisely the problem we have now for high-performance computing. And this problem is that you have a lot of computing power, but every time you try to access the memory, you can lose cycles, hundreds or maybe even thousands of cycles if you try to access like a hard disk drive. This is a problem. Because now we need to optimize the codes for cache and memory access. And in this simulation, the adaptive mesh refinement is implemented in terms of explicit trees, which means that every cell is a node of a tree, and the nodes are linked together by pointers. The problem with that is every time you want to access a node, you go elsewhere in the memory, and it's not at all cache efficient. So they started to think about what they could improve about these trees. So they started with numerical cosmology, and numerical cosmology is based, as I said, for a large part on octrees. And octree is just adaptive mesh refinement in 3 dimensions. But if you improve octrees, this can have consequences for all kinds of physics simulation and also for visualization. But octrees are a kind of spatial trees, and spatial trees are used for geomapping and spatial search. Spatial trees are a type of trees, and trees are used everywhere in computer science, including machine learning and language processing, and even compilers are based on trees. And now in Urbana-Champaign, we have a whole team, I lead a whole team about making trees far more efficient. It's the Tree Building Block Research Project. There are types of trees that are implicit trees and where you can create them as associative maps. It's very efficient, but there is a problem of them that the key, so you have a pair of key and values, but the keys to be efficient have to be sometimes more than 64 bits. And the problem is that we don't have anything to deal with more than 64 bits in either a static or dynamic way in C++. And this kind of integral bit set can be used in a lot of areas like arbitrary precision and arithmetic. To implement that, we need bit manipulation. And for that, we need to start from scratch about bits. And this thing can concern a lot of areas in computer science, particularly if you want to have very good performance. So they soon realized that to make the most efficient trees ever, they would need very efficient ways to manipulate bits. And this is how the whole story started. Thankfully, the old magician of C++ land came to them and helped them to start their quest. He gave them a very precious map and disappeared. And that map was the following. It's a map of the C++ language, and you have everything is there. So they started to search what do we have in the standard library to deal with bits. And they started to search around here because it's about the bitwise canyon, so you have bitwise operations. And then they looked more closely, and they saw these things, Electroball and BitSet. The problem, it doesn't look very appealing, but this is the only thing they found in that map to deal with bits. So they decided to go there with the hope to leverage some bit manipulation to speed up their trees and their simulation. And this is where the bit manipulation library started, how it started. So now I will describe the current status of bit manipulation in the C++ standard. So first, let's start with BitSet. So I guess all of you know the BitSet class. So if we look at CppCon reference, it tells us that it's a class template to represent a fixed sequence of n bits. And on that sequence, there are some operations we can do. So this is the example given from CppCon reference. So first, you declare a bit set with 8 bits in it. You print the first value. Then you try to find with a while loop the first unset bit, so the first bit at 0. And for that, you use the bracket operator. You can use the bracket operator. And then what this program do is it will set bits until half of the bit set is filled. And to do that, it uses some function like bitset count and bitset size. And you end up with the bit set that is written here, second one. So it's very simple and easy to use, and there are some optimized function members like test, all, any, none, count, set, reset, and flip. The problem is that you only have that, so it's very limited in terms of function and functionality. For example, you don't have any begin or end iterators, which means that this container is not really a container because it's not compatible with standard algorithm. And you have no control on the underlying representation. BitSet is generally implemented as an array of unsigned integers in which you store your bits. But the problem is that you don't have control through a template parameter. So if you want to do your own bit manipulation, you can't really do it. There are also something about the operator bracket on BitSet that's a little weird. So in that small program, we create a bit set of 8 bits, and then we set it to 42. Then we create a Boolean value, a bool, from the first element of that bit set, and also something that is with the keyword auto, which means that we have a reference to this first element. And then on Boolean, we can do plus equal 1, and something we cannot do plus equal 1. So it's a little weird. What's happened is that operator bracket returns a proxy of type. It's a nested class, which is called BitSet reference. It's almost like a bool, but just almost. There are different promotion rules, different arithmetic, a member flip, and different behavior of operator bitwise not. And this is extremely confusing and error prone. For example, so here we declare a bit set of 8 bits, and we set it to 0. Then we do the same as in the previous slide. We declare a Boolean value, and we declare something that is a reference to the first element. Both of them are set to the same value. And then we do 2 bitwise NOT on these things. And we print first the Boolean value, and then the something. So which means that we start from 0, we apply bitwise NOT, it should set it to 1, and then we apply it again, it should set it to 0. Pretty simple. So, but is that this simple? So what does that print? Who thinks it prints 0 and 0? Okay. Who thinks it prints 1 and 1? Who thinks it prints 1 and 0? Okay. And 0 and 1? Okay. Some of you think 0 and 1. And it's 1 and 0. The following happens. So you start, and the first thing, you start from a bool value. This bool value is 0, so the first operation you do is bitwise NOT and false. There are promotion rules in C++, and when you execute bitwise NOT and a Boolean, it converts it to an integer, which means that not false gives you -1. Then what you do is you bitwise NOT this -1, and bitwise NOT of -1 in integer for an integer gives you 0. And then you store this 0 in Boolean, and you end up with 0. Now with the reference. So you start from 0, you bitwise NOT it. It gives you a Boolean, which is true. And then you bitwise NOT it again. The problem is, at that step, it's converted to an integer, and true is 1. So you do bitwise NOT on 1, and bitwise NOT on 1 is -2. And when you convert back -2 to a bool, it's considered as true. That's why you end up with 0 and 1. So this kind of behavior is very misleading. Then we have another thing to manipulate bits in C++, which is vector bool. So my opinion on vector bool is that it's one of the biggest mistakes in the standard. If we look at what CppCon says about vector bool, it says the following thing. Vector bool is a space-efficient specialization of std vector for the type bool. The manner in which vector bool is made space-efficient, as well as whether it's optimized or not, is implementation defined. One potential optimization involves coalescing vector elements such that each element occupies a single bit instead of size bool bytes. Vector bool behaves similarly to steady vector, but in order to be space-efficient, there are 4 things now. It does not store its element in a contiguous array, which is completely different than the standard vector. Then we have vector bool reference, which acts in the same way as BitSet reference. It does not use the allocator trace construct to construct bit values. And finally, you have no guarantee that different elements in the same container can be modified concurrently by different threads. It's because std vector can be implemented as an array, a dynamic array of unsigned integer. And the problem is, let's say you want to write at the same time by 2 different threads the first bit and the 5th bit. The first and the 5th are likely to be contained in the first integer of the sequence of your dynamic unsigned integer array. So when you will try to modify them at the same time, you will access the same underlying integer at the same time, and it will fail. So vector bool is not a container, it's not conforming the standard, even though it's in the standard. And there have been, in the past year, since 1999, there have been a lot of papers trying to correct what's wrong about vector bool. And the problem is that still, in 2016, vector bool is still alive. So we need something to replace it. The good thing about vector bool is that it's a compact storage in memory, and you have begin and end iterators, so it's compatible with standard algorithm. there are a lot of problems. You have poor performance, no access again to the underlying representation, no thread safety. It breaks the normal behavior of containers, and you have the same problems as with bitset reference. It's not a problem of the functionality of vector bool, because the functionality is okay, but the mistake that was made is that it should not be a specialization of vector. It should be an independent dynamic bitset as we have in Boost. So we have these two tools, but the problem is that in bit manipulation can be useful for a lot of things, and particularly new generation of processors, you have intrinsics, assembly functions that can be used to speed up some applications. And these intrinsics can be used, here you have a plot of where it can be used. So for example, in cryptography, bioinformatics, in error correction for memory, and these kind of things. On modern processors, as I said, there are new instruction sets that leverage bit manipulation to do things very quickly in a short period of time. It replaces sometimes tens of bitwise operation by a single assembly instruction, which means that it can really optimize the code that use these kind of instructions. Here I listed some of these instructions. For example, PopCount. What PopCount does, it counts the bits in an unsigned integer all at once. So some people wonder how can we improve bit manipulation in C++. And there was a proposal in 2014 that was called a ContextPerBitWiser operation library for C++. And the goal was to give a standardized function like that to manipulate bits. The problem is that there was more than 60-bit specialized function. They were operating at a very low level, and they were limited to small range of arguments, mostly unsigned int and unsigned long int. And it didn't provide any tools to manipulate arbitrary long sequence of bits. So the bit library started with this thing, and we wonder how can we make things far more generic to operate in bit sequence. So the bit library.
Just one question.
Yeah.
I've done a lot of work with the Boost Dynamic Bitset. You briefly mentioned that one of the frames. But can you take just a few seconds to talk about what some of the issues with that in this context?
So BitSet, Dynamic Bitset also provides a structure that generalizes the static version of it. And it has the same kind of problems about the reference. There is no a coherent set of tools to manipulate bits. So you have bit iterator, you have bit reference, but it's hidden from the user. And if you want to implement your own bit manipulation algorithm in a very efficient way, you need access to the underlying representation.
Well, one of the things it did give you is the ability to provide the buffer, the underlying storage for it. So I guess you could go back and forth, but I think some of those other problems.
What we designed could totally interface with what Dynamic Bitset actually do. It's like generalizing what's already done in this structure, but sometimes it's hidden from the user.
That was on purpose, by the way.
Sorry?
That was intentional.
Yeah.
Hiding it from the user.
Okay. So the idea behind that is to this library will act as an underlying layer, a common layer that can be used to reinterpret sequence of unsigned integer as sequence of bits. And on top of that, as I will explain, we can implement a bit view, bit range, and bit container adapter to adapt whatever container you want to a bit container. So as I said, the goal is to make the most of bit manipulation instruction sets and sequence of unsigned integer. To be able to give people the tools to implement their own bit manipulation algorithm and bit-based data structures. As I already said, there are a lot of application areas. And here I listed some concrete example of use. For example, user-defined sets and bit arrays. With what we provide here, it should be very simple to implement them. An access to the underlying bits of bounded and unbounded integers, and allowing people to implement their own algorithm. For example, here a specialization of count that called the CppCon instruction when executed in bits. It resonates also with something that Bjarne said about the fact that unsigned integers are types that are ideal for use that treat storage as a bit array. The problem is that there is no standard way to access and manipulate bit arrays in C++ and to treat unsigned integer as bit arrays. What we want to do is to give user tools something simple, generic, and efficient. So the solution, the key idea is that the thing that is very at the center of this library is a bit iterator. All of what I spoke about can be achieved through a carefully designed bit iterator, acting as an iterator adapter, like std reverse iterator. It's the same kind of things. So a bit iterator takes another iterator as a template, and it provides people with an API that is both high level and low level. From the high level, it's easy to use from the general user point of view. From the low level, it gives access to the underlying representation for optimization purpose. So from the high level, what you can do, for example, is you create a list of unsigned integer with 0, 1, 2, 3, 4 in it. And then you create a bit iterator that is, for example, starting at the first bit of the first element, the fifth bit of the first element of the container. And you want to end your sequence on the last element of the container. And then if you can execute the standard algorithm on this sequence in between first and last, for example, to count the bits that are set to 1, and it will return the number of bits that are set to 1 in a very efficient manner. Regarding to design, there are two questions that we needed to solve to implement this library. The first one is about what representation we are talking about. In C++, there are two representations. There are object representation, which deals with memory, how bytes are stored in memory, and the value representation. For example, if you set unsigned int to this value, the object representation is different from the binary value of the value representation of that unsigned integer because of little endianness. It would be different on a big endian machine. But if we design something that is dependent of the underlying memory representation, then the result will be different on different architecture. So we decided that the bit, when we say we want a bit at position 0, it refers to the binary, to the value representation in binary, which means that we are only able to operate an unsigned int because, for example, on integer, there is no specification in the standard where the minus sign is, where the sign is. Same thing for floating point values. So our library is focused on unsigned integer. And regarding to the move we can do with bit iterators, it's done that way. So for example, if we create a list of 4 integers that I listed here in binary, starting from the LSB on your right and the MSB element 31 on the left, and let's say we set an iterator to the thing that is in red. So if you decrease the iterator, you will go that way, and then go on the continue to reiterate on the first integer of the sequence. So if you do your bit iterator minus 23, you will have the green, an iterator to the green element. Reverse thing for if you do the thing in the opposite way, if you do your iterator plus 55, you will end up with an iterator to the yellow cell. Now, from the low-level point of view, there are three key functions that you need to know to be able to implement the bit algorithm. So first, an iterator has a member base. It's the same kind of base as reverse iterator base, and it returns the underlying iterator. Because, as I said, bit iterator is an iterator adapter. Then a bit iterator also gives you a member position, which gives you the current position of the bit within the value it refers to. You have the same member function on a bit reference, and I will explain this later. And then a bit reference, you have also a member address that gives you a pointer to the underlying value. So, for example, if we want to implement a specialization of the count algorithm for bits, so let's do the implementation for a bit iterator first, a bit iterator last, and a bit value. So you started. So here we just declare some types, and we control if the sequence is good. And then we have two cases. The first one is when your bits are in different unsigned integer. Second case is when your bits are in the same underlying integer. So in the first case, what you do is you check whether you start at the LSB of your integer. This is what does bit position different than 0. If it's different than 0, it means that you're not aligned. And what you do is you shift your first integer and you count the remaining bits. Then on the unsigned integer that are between first and last, you simply iterate on the sequence and execute a CppCon function on them. And then if you have remaining bits on the last integer, you do the same as before. You shift your integer and you count the remaining bits. Where your two bits, first, your 2-bit iterator are on the same underlying integer, then you do something a little more tricky. You extract the middle part of your unsigned integer, the part in which you are interested, and then you count the bits in that sequence. And then depending whether you want the number of ones or the number of 0, if you want the number of 0, you simply compute the difference between the number of bits you have in the sequence and the number of ones. And you give back the result. And so with bit iterator, it's easy to manipulate from the user point of view because you simply declare your bit iterators as an iterator adapter. But it also gives a standardized interface to access the underlying sequence. But there are key design questions. Because it's an iterator, we need to answer this following question. What is difference type, iterator category, value type, reference, and pointer? The easy ones, iterator, bit iterator difference type can be implementation defined, but should be at least as large as PTR GFT. For iterator category, it's the same category as the category of the iterator you pass to bit iterator. And the difficult ones are what are the value type, the reference, and the pointer type. Here, to answer this question, this figure summarizes the main tools we have in the bit library. So we have a bit iterator, as I said, that can, with an operator like dereference and bracket, and this operator will give you a bit reference. That's the reference type of bit iterator. Same thing for bit pointer. Same thing for bit pointer, and if you execute the bracket operator on a bit pointer, it gives you a bit reference. But sometimes we also need to deal with bit values that are not referenced in an unsigned integer, but which are independent. This is why we have also a bit value. And then we have three helper things, a 0 bit and 1 bit, which are just a bit value that are ContextPer and defined as 0 and 1. And binary digits that in most cases return numeric limits of unsigned integer and the number of bits. But if users want to provide a template specialization for that, then they can only provide a specialization for binary digits and not affect the numeric limit digits.
What is the type of 0-bit and 1-bit?
They are bit value. They are declared as bit value.
Thank you.
So now I will go to some tricky details. So when we started to think about this, we wondered, what is a bit? This is an innocent question, but it's actually very complex to answer. Related questions are what functionalities a bit should provide, and what should be the arithmetic behavior of a bit. For example, we see, as I already said, in BitSet and vector bool, a bit is defined almost as a Boolean value, but it leads, as it's only almost, it leads to some problems. For example, with the bitwise not and operators with assignment operators with also plus, equal, things like that. And currently in the standard, it's actually a mess, because if we compare the results, the behavior of a Boolean, a bit set reference, and a bit field, it leads to different results for some operations. Some of them don't even compile, where it's the line where I put X, but for some operation, the result is not the same. So already in the standard, we don't have a clear agreement on what a bit is. According to the C standard, a bit is a unit of data storage in the execution environment large enough to hold an object that may have one of two values. According to the C++ standard, a bit is an element of a contiguous segment forming a byte being the fundamental storage unit in the C++ memory model and being at least 8-bit long, which means that you can have more than 8 bits in a byte. And some weird architecture. If we look to Wikipedia for a tentative of mathematical definition, the bit stands for binary digits, a digit being a numeric symbol used in combination to represent numbers in a positional numeral number. And if we look to a Boolean data type is a data type having two values, usually denoted as true and false, intended to represent the truth values of logic and Boolean algebra. So there are bits, and bool doesn't seem exactly the same. And I think one of the key ideas to try to implement something that is working and not misleading with a clear behavior is that a bit is a binary digit, a Boolean is a logical data type, but a bit is not a bool. They are often identified because they just both happen to have two values, but the logic behind it is different. And if you are not convinced, if bit and bool were the same, we would not have the problem we have with vector bool, and an array of bool and n should be the same as bit set. That's not the case. So now I will solve the question about what the types nested in bit iterator should be. So the value type of bit iterator is a bit value. It represents an individual bit, and we named it bit value because it mimics the behavior of a bit, but it's not actually a bit in memory, since bit cannot be represented in memory. So it's stored in another way. Like, for example, it's just a wrapper around the bool. The make functionalities are that you can take an unsigned integer on a bit position and you can construct from that your bit value. There is no arithmetic behavior to avoid any kind of confusion. This is the same approach that is currently studied for std byte. You have bitwise operators, you have a flip, set, and reset numbers, and if you want, you have an explicit conversion to bool. And here I illustrate some of these functions. So here we take the bit at position 1 in 3. We flip this bit, just to illustrate that we can use the flip function. And then we set the bit value to the 0th bit of 1. We set it to 1, and if we print this value, it's 1. Yeah.
Seems like the statement about no arithmetic behavior is actually contradicting your previous slide. If it's a binary digit, you should be able to add 2 of them. On the other hand, if it's a logic type, then you shouldn't. So this became more like a logic type.
So we came to the committee with 2 different propositions. One with an arithmetic behavior and the other one without. And we asked the committee what he liked more. The thing in the mathematical definition, it's a numeric symbol. It's not an actual number. It's a numeric symbol. And to avoid any kind of problem we already have with bool, with arithmetic bool, they decided we prefer to restrict the arithmetic behavior so we don't have any kind of weird conversion happening. And in most cases, except if you implement your own bit manipulation algorithm, you won't have to do it with bit value. We need it because you need it to make a bit iterator that is well designed. But in most cases, you won't do weird things with bit values. Then for bit reference, we have, for the type reference in bit iterator, we have a bit reference, which acts the same way, except this time it takes a reference to an unsigned integer and a bit position. We overloaded the operator and to return a bit pointer. And it has an address and a position that can tell you it gives you an access to the underlying representation. So in that program, we declare an unsigned int at 4. We create a reference to the 3rd bit of this unsigned integer. We flip it, and then we print the result. So the result so now the reference bit is set to 1. If we print the position of the bit, it will print 3. And if we access the underlying integer, because we set the bit to the 3rd bit, it's now 12. And finally, a bit pointer, which is complementary of bit reference. It mimics a pointer to a bit. This time it takes a pointer to an unsigned integer and a bit position for construction. And we overloaded the operator star to return a bit reference. So they are very complementary. So for example, if we declare an array of 2 unsigned integers, and we declare 2 pointers, the first one, oh, I made a mistake. The first one is on bit number 3 of the first element. The second one is on bit number 8 of the element 1 of the array. Then we flip the first one, the first bit, and if we print it, it leads to the same result as in the slide before, as with bit reference. Same thing for position and address. And if you compute the distance in bits, because you have your 2 unsigned integers are in the same array, it gives you the distance in bits between the two bit pointer, which is in that case 37. And finally, we have the binary digit structure helper, which is just it inherits from integral constant. It tells you how many bits you have in unsigned integer or in a user-defined type if the user defined it. And as I said, the bit iterator combines all of that to bring capabilities of bit manipulation and to leave user with the opportunity to manipulate bits, either from a high-level point of view or from a low level. And as I showed in the general design, the operator star of a bit iterator returns a bit reference, and you have the base and position numbers that gives you an access to the underlying sequence. So this is the example I showed, I think, on the first or second slide. So you declare, here you declare a list of unsigned integer. You create first and last iterator, and then you can count the bits in between. The advantages are the following. It's easy to use, generic, and efficient. It's very generic because it allows you to reinterpret any kind of sequence of unsigned integer as a sequence of bits. There are zero overhead with minus 0.02 and minus 0.03. Most compilers are able to optimize the abstraction away. And it has a very good integration with the existing standard library. It's like it's an iterator adapter as reverse iterator, and the interface allows you to interact in the same way with as you do with standard iterator with standard algorithm. So now I will speak about some benchmarks we did. First, I would like to say that Howard Hinand made a great article about this kind of bit manipulation in 2012. He was already mentioning something a lot of things that we are describing here in the bit library. The web page bit twiddling hacks is really, really useful when you want to optimize a bit manipulation algorithm. And the implementation of reverse I will show was done with a student, Magav Kumar, at the University of Illinois. So if we compare for several algorithms that we optimized with our interface compared to what GCC can do on Victor Bool, we have the following comparison. So on the x-axis, you have different standard algorithms, and on the y-axis, you have the average computing time per bit in seconds, and the scale is logarithmic. On the top, you have the speedups, and we do average for several computation over 100 million bits, and it was on an i7 2630 QM. It was on a laptop. So the kind of performance we can obtain are very, very good. In most cases, we have several orders of magnitude of improvements. For example, with PopCont, with count, STD count, we have almost 100. With copy, we have 522. With sort, we have more than 3,000. Because sorting, when you know that you have only two values, you can just count the values and replace the underlying values of unsigned integer by the number of 0 and 1 you have. The trick behind all of that is instead of operating on a bit at each time operating on a single bit, is that you can operate on 64 bits at a time, because most of the time you have compiler in tracings and assembly function to do that. And if we plot it in a non-log scale, you end up with something like this. We don't even see the bit iterator performance in that plot. So these preliminary benchmarks were done with aligned bits, and we are now working on implementing the algorithm for non-aligned bits. So when your bit iterator does not start at the LSB, and neither your first and last iterator are corresponding to least significant bit. And here an example of the implementation of STD reverse it's kind of tricky. So I will just describe it in a general manner. And if you want to look at it, it's in the, just download the library or look at the slides, and they will be available, and you will see how it's done. So basically, we want to reverse a sequence of bits. So when bit iterators corresponds to LSB, both first and last, then it's easy because the thing you can do is you can just reverse the integer, the underlying unsigned integer first, and then you reverse the bits within each integer. So what we do is we call the reverse algorithm, the standard one, on the underlying sequence of unsigned integer, and then we call bit swap on each element. The implementation of bit swap is tricky, but if you want to look at it, it's in the library. Then when we have when the two iterators are referring to different integer, underlying integer, and at least one of them is not corresponding to a least significant bit. So I won't go into detail, but what we do is we start by reversing the whole sequence. And then first we save the values of the first and last integer. Then we reverse the whole underlying sequence. We shift it then by a given number of bits if necessary, so either to the left or to the right. Then we bit swap every element in the underlying sequence. And then we replace the first and the last element by the value we saved. So we mixed the bits of the value we saved and the bits that we inherit from reversing the sequence. And then the last case is when the bit iterators belong to the same underlying value. In that case, this function does a mix of bits according to a mask, and it's actually very efficient. So if we study the performance of this new version of STD reverse, so it works on all kinds of sequences, not only LSB, but we are still working on adapting the other algorithm of the standard library. And in that new version, the low-level function like bit swap have been improved thanks to the bit twiddling hacks using compiler intrinsics and using template metaprogramming. So in the first version, we had 31 performance improvement, and with this new version, we have 86 performance improvement compared to Electroball. So in summary, the interface of Electroball is broken, and the one of BitSet is very limited. Bit iterator is a good way to combine the ease of use, genericity, and performance. And in terms of performance, as we have seen, if you implement the standard algorithm to use compiler intrinsics, you can have several orders of magnitude. We have seen also that abstracting bits is not an easy task, and we asked several times the committee their advice on some questions. For example, what should the arithmetic behavior of a bit should be. The bit library is a still work in progress. So we are now working on, as I said, on the specialization of most algorithm. And there are still some work that is ongoing on bit value and bit reference because there are some open questions for standardization. The library is available online for everyone to test, benchmark, share, and participate. So you are very welcome to test it. Regarding to standardization, the proposal and wording, the number of the proposal and wording is P0237. It has been submitted several times. The feedback is pretty good. There are still some issues that will need to be solved, but we hope that this bit iterator adapter will end up in the standard library for C++ next. At least that's what we hope. Regarding to open question, two of them are particularly tricky, I would say. First one is someone in the last committee meeting, someone asked whether bit value should be a template class so that we can implicitly convert reference to bit value to bit references. The situation about that is still not very clear, but we are trying to see whether it would be a good decision or not. Second question is far more tricky, and I spent hours thinking of that, and I don't have the solution. So template and CV qualifiers do not combine very well for proxy classes such as bit abstraction. So if you declare a bit reference on a const t, there is no problem. It's a const reference and it behaves as a standard constant reference. But when you have both template and CV qualifiers, you can declare something like a const bit value of a volatile t or a const bit reference on a mutable t. What should happen with these kind of things? Particularly regarding to the conversion between these types. Because now, can we convert, like, what happens if we take a reference to a bit value that is constant volatile? What types of reference does it give? So if you have any clear view on that problem, please come to me and contact me, because now the situation is not very clear. In terms of future directions, as I said, we will work on the standard algorithm. We are also working on bit range proposal to adapt with the new range proposal, to adapt our interface with the new range proposal. After that, we will implement container adapters to reinterpret containers as static or dynamic bitset. So, for example, you would be able to declare a vector of unsigned int and then treat that as a dynamic bit containers. And after that, we may work on multi-precision integer arithmetic. Finally, here are some people we would like to thank. So the drawings were stolen from XKCD by Randall Munro. We are thanking the C++ community for all the feedback we had for standardization. And this work was done in the tree library, in the tree building blocks library team, which is in the data science group of the Department of Astronomy of University of Illinois at Urbana-Champaign. And our goal is to end up with trees to optimize both high-performance computing simulation and big data science and machine learning algorithms that are based on trees. Thank you for your attention. Any question?
Are you able to use this in any sense yet in your cosmological simulations? Are there subsets at least that you can throw this at that it helps with?
So it's a long-term project, and what we want to do, we are starting to use that to implement a class that is called integral bitset. It's like a bitset, but it also provides some kind of arithmetic behavior, multi-precision arithmetic. And then with that, we will be able to build implicit trees that are associative arrays of keys and values. And on top of that, then we will be able to implement adaptive mesh refinement, and we expect order of magnitudes of improvements in terms of performance compared to the current explicit trees.
Are people still using the vector bool even though it doesn't necessarily work?
I hope not. I would encourage everyone to stop using vector bool and replace it by something different in their code.
A lot of them are using Boost Dynamic Bitset.
Yeah. Boost Dynamic Bitset is perfect to replace vector bool.
So I guess this is a little bit related to that open question of whether value type ref should convert to bit value should convert to bit reference. But it seems a little bit more subtle than that. You said that the iterator category is determined by the iterator inside, what you're wrapping. So it's the same iterator category. And you also said that the reference type of the iterator is bit reference and the value type is bit value. But when you have a forward iterator, or anything more refined than that, the reference type has to be exactly the value type ref or const value type ref. How do you plan to address that in your proposal?
So the question is, how will we address the conversion between reference to bit value and bit reference on things like forward iter? Is it
not exactly the conversion? It's that
specification.
Yeah, it has to be exactly that type.
So the answer to that is the range proposal, and particularly there is something called there is a proxy iterator proposal that wants to give generic tools to deal with proxy iterators and make people able to deal with this kind of problems. It gives, so I don't know this proposal by heart, but you can specify how does the reference and value and reference type are linked all together.
So as a follow-up to that, are you targeting post ranges TS? You said C++ next. Is this a separate proposal from ranges TS, or do you actually depend on that?
The question is whether we are targeting the same. Are we targeting the range proposal? The answer to that is, for now, it's an independent proposal, but we have discussed things so that we are sure that our interface is compatible with the range proposal, so that as soon as we have ranges, we will define bit ranges, and this interface will interact perfectly with the range proposal.
Question. So since we now have concurrency in the standard, there are kind of two parts to it. One, you have to at least say something about the memory model of that thing. If I don't say anything else, at least, what do I get? You can say you get nothing, but you have to say something about the memory model. And the other one, are you going to give, like, either specializes to the atomic for it or give me an atomic version of it? Some processors actually have atomic bit instructions.
The question is what we will do about concurrency concerning these bit utilities and how we will specify them. For now, we are focusing on the single-threaded version, but we are working on providing specialization of the algorithm that are not multi-threaded, but then we will work on the algorithm that are multi-threaded, and while we are doing that, we will realize what we need.
What I do a lot is to, during coding, like CppCon and that kind of thing, is to rewrite machine-specific integer sizes, integers like 5 and 8, but it comes from like 32 bits. Then you rewrite that as a string of integers of some other arbitrary size, like 11, okay, depending on the entity of the input data and that kind of thing. So is there sort of in the future direction where that would be made much easier? Because currently, I always have to convert from one integer type to some underlying integer type, and then there's a little while loop, and then you write this, one part of it in there. If it's over a boundary, then you chop it up and shift it a bit, and then you write the next boundary and carry on like that. So there's a lot of modulus arithmetic and shifting going on that I have to go manually. Which is it sort of in the future? Because I see that the bit iterator interface sort of starts addressing that problem, but writing the arbitrary length integers is sort of a bit off. It's not really, you're not writing bits, you're writing symbols of arbitrary length to a bit stream. Right, so it's sort of like a serialization exercise actually, but if there's some direction in the future where this will be made much easier.
So your question is about is there some direction with that library to deal with interacting with two different types of unsigned integer and to stream the bits within integers?
Yeah,
correct.
So in other words, I want to define my own unsigned integer type, which is 11 bits long.
Okay.
And then write that in 11 bit segments to a bit stream or whatever under some other underlying representation of whatever arbitrary machine. So it converts from 11 bits to segments of 11 bits within 32-bit integers.
So how do we deal with segments of 11 bits? So are you speaking of architecture that has integer of 11 bits, or are you storing the 11 bits integer, for example, as an array of unsigned char?
I can't really store 11 bits.
Okay.
In a working format. I keep it in 32 bits. Then I know as the programmer that only the first 11 bits of that 32 bits is significant. In fact, take that symbol and then write it out to the bit iterator.
So,
Incrementing that 11 all the time.
Okay. So to deal with, for example, an 11-bit integer that is stored as a 32-bit integer, what you would do is you would create an unsigned integer. You would create a class that is defined to be an integer of 11 bits long, and in that you will store your 32 bits long integer, and you will interpret, thanks to bit iterator, your unsigned integer as an 11 bits integer.
And that's what BitSet does right now.
Yeah. More question? Yes.
Have you measured the performance on non-Intel platform?
On none?
Intel-based platform, like ARM or something like that?
For now, so most of the algorithms are for each. So the question is, can we deal right now with architectures like ARM? The goal is to be able to do it. For now, we focus on x86 and 64 architectures. The thing is that most of the very efficient function like bit swap things like that. We have a version that works everywhere on any architecture, but on some architecture we have version of that function that use intrinsics. To make the thing working on ARM and using the intrinsics of ARM, we would just need to I guess, to make these very fundamental functions call intrinsics on ARM, and that's it. Okay, thank you very much.